We're in Unit 3, Block 4, starting example 3. We're given a function f of x, which is the profit in thousands when they spend X dollars on advertising that day. We're asked to find local maximum, local minimum, and inflection points, and we'll also do some interpreting when we're done. First, let's go ahead and start by finding local maximum and local minimum. In order to do so, we're going to have to identify the derivative and find critical points, places where the derivative equals 0 or where the derivative is undefined. So I notice in this function f of x, it's a product of a linear and an exponential. So we're going to use the product rule. The derivative will be 50 times e to the negative 0.04x plus 50x times e to the negative 0.04x times negative 0.04. I'm going to go ahead and rewrite that a little bit. I'm going to simplify it down a little bit because I know I'm going to have to solve it for where it equals 0. I notice that there are two terms in my derivative. This term over here, 50 e to the negative 0.04x, and this term, 50x e to the negative 0.04x times negative 0.04. I'm going to factor the common factors out of these two terms. I notice they both have a 50. They also both have a factor of e to the negative 0.04x. I factor the 50 e to the negative 0.04x out front. That leaves 1 plus x times negative 0.04 when I factored the 50 e to the negative 0.04x out. In other words, f prime of x equals 50 e to the negative 0.04x times 1 minus 0.04x. I found the derivative. Now I need to find critical points. Critical points are places where the derivative equals 0 or where the derivative is undefined. In this case, the derivative is defined for all x's. You can plug any x into this function and you will have a real output. So I only need to focus my attention on finding the x's that make the derivative equal 0. What I have here is a factored expression set equal to 0. When you have two factors multiplied together and the answer is 0, the product is 0, it must be the case that either this factor is 0 or this factor is 0 or both. So I set each factor to 0, and now I need to solve. So first, the one on the left, 50e to the negative 0.04x equals 0. This has no solutions. There are no x's that's going to make this exponential function equal 0. Exponential functions never hit the x-axis. Exponential functions never equal 0. So we can disregard that one. Instead, I can focus my attention on solving 1 minus 0.04x equals 0. So we're just adding 0.04x to both sides, dividing both sides by 0.04. So we get x equals 25 when you divide it out. This is the only critical point. Again, every time that you're going through and doing your solving, you need to make a sentence explaining what you've just learned. So we set the derivative equal to 0, and we found this one critical point. That's the only one that exists. That means f of x flattens for an instant at x equals 25, and that's the only place f of x flattens. I'll also note, since this is a critical point, x equals 25 is a potential maximum or minimum point. Now, since this is business calculus and we don't have such a strong emphasis on algebra as we do in a traditional calculus class, in a problem like this one, where you were trying to solve where this f prime equals 0, it would have been okay if you went ahead and did this in Excel. You could have used Solver in Excel, if you like, to find when that derivative equals 0. So in this sort of problem, I would accept that. You could use Excel to solve, or you could solve it by hand like I just did there. All right, we know that we have this potential max or min at x equals 25. At this point, I'm going to go ahead and use the first derivative test to test and see if f of x actually turns at x equals 25. So I'm going to pick a value to the left of it, like x equals 0, plug it into the derivative. I'm going to pick a value to the right of it and plug it into the derivative. And Here we go. I picked x equals 0. We're going to plug x equals 0 into f prime. So it doesn't matter. You can plug it into the original f prime, or you can plug it into the factored form of f prime. When I plug x equals 0 into f prime, I get f prime of 0 is 50. When I plug x equals 30 into f prime, I get f prime of 30 is negative 3.012. So on the left side of x equals 25, since f prime is positive, f of x is increasing. Then at x equals 25, f of x is flat. Then, since on the right side of x equals 25, f prime is negative, we know f of x is decreasing. So at this time, I can now conclude near x equals 25, we have increasing. Then at x equals 25, it's flat. Then on the right side, it's decreasing. This is what f of x must look like near x equals 25. So x equals 25 is a local max. Next, the problem asked us to identify inflection points. So I just noted here what we had already solved on the previous page was we found f prime of x. And so now we have f of x, f prime of x. We know if we want to find inflection points, we're going to need f double prime. So we need to find the derivative of f prime. Again, f prime is a product. It has one factor times another factor. And we're going to go ahead and use the product rule to find the derivative. So I find the derivative of this first piece is 50e to the negative 0.04x times negative 0.04 times the original second function there, plus the original first function times the derivative of the second function. I'm going to go ahead, since I'm going to be solving by hand, I am going to rewrite this a little bit. Again, though, in this class, if you prefer, at this point, you could just pop this thing in Excel, and when you want to find when the second derivative is 0, you could just use Solver to find when this thing equals 0. I am going to go ahead and solve this by hand, so I'm going to factor out any common factors. Notice there are, again, two terms. There's this first term here that I'm underlining, plus this second term here that I'm underlining. So I can factor out common factors from the first term and second term. They both contain a factor of 50. They both contain a factor of e to the negative 0.04x, and they both contain a factor of negative 0.04. So I factor that out front. I pulled it out of the first term, which gets rid of the 50 and the e to the negative 0.04x and the negative 0.04 in the first term, leaving the 1 minus 0.04x, plus I pulled out the 50 out of the second term, the e to the negative 0.04x out of the second term, and the negative 0.04 out of the second term, which leaves 1. Simplifying that, first I'm going to multiply 50 and the negative 0.04, just actually write out what we get there. When you multiply that together, you get negative 2. And over here, inside the parentheses, we have 1 minus 0.04x plus 1, so really it's 2 minus 0.04x. So there is my simplified factored f double prime of x. Again, at this point, you could pop that in Excel and solve where it equals 0. We're trying to find inflection points. Inflection points occur when f double prime changes sign. Places where f double prime can change sign are places where f double prime is 0 or where f double prime is undefined. This particular f double prime is defined for all x's. No matter what x you plug in, you'll get a real answer out. So we only need to focus our attention on solving where f double prime is 0. Again, you can pop it in Excel and solve. I have it in factored form. One factor times another factor equals 0. In order for that to happen, it must be the case that this factor is equal to 0, which can never happen because it's exponential. Exponentials never equal 0. Or it must be the case that this factor over here, the 2 minus 0.04x, is equal to 0. Solving that, I get 2 equals 0.04x. Dividing both sides by 0.04, we get 50. This is a potential inflection point. You're not done yet, though. You have to actually prove that it is an inflection point. We're going to draw that number line, and we're going to check to see if the second derivative changes sign at that value. I pick a value on the left side, and I plug it into the second derivative. So f double prime of 0. I pick a value on the right side and plug it into the second derivative. So maybe f double prime of 55. When I plug 0 into the second derivative, I get f double prime of 0 is negative 4. The second derivative is negative. That means f of x is concave down over here on the left side of x equals 50. I plug 55 into the second derivative. I get 0.04. The second derivative is positive. The second derivative is positive. That means f of x is concave up. We have now tested and found that x equals 50 must be an inflection point because at x equals 50, the second derivative is 0, and the second derivative changes sign at that value. What we've now learned is that we have an inflection point at x equals 50, and on the previous page, we found that we had a maximum, a local maximum at x equals 25. This was a profit function where we were plugging in x's that represent advertising dollars, so x cannot go below 0. So thinking about x equals 0, you'll see when you plug 0 into f of x, f of 0 will equal 0, so it actually goes through the origin. It's just giving us a nice starting place for our graph. F of x goes through 0, 0. We learned that if you go over here to x equals 25, you will have a maximum, and that is the only critical point on the graph, the only place where this thing flattens. So it increases, flattens at its peak at x equals 25, and then ever after it decreases. But what we also saw here was that at x equals 50, it changes from being concave down to being concave up. What you'll actually find is that it looks like this.